Assalamualaikum all. For Chapter 4 Network Layer Part 3, we are going to learn about classful addressing. So, classful addressing is actually not part of the syllabus. Classless addressing is part of the syllabus. However, to understand classless addressing, we need to know first about classful addressing. So recall back the position of the network layer in between the transport layer and also link layer at the TCP/IP protocol stack. We have learned about the IP protocol in terms of datagram format. Now we are going to learn about the addressing conventions and how we want to allocate addresses for all the hosts in the network. And after that, we will learn about the ICMP protocol as well as the routing protocols. Okay, moving on to the next slide. We know that every host and router on the internet has an IP address. It can be used as source address and also destination address, the IP packets. So basically, IP address is an identifier in the IP layer to identify devices or hosts connected in the network. The address is unique and universal. So they are unique in the sense that each address defines one and only one connection to the internet. So there will be no two devices on the internet that can have the same address at the same time. So the keyword here is this: they cannot have the same address at the same time. But however, if a device has two connections to the internet via two networks, it will have two IPv4 addresses. Okay, so the address space here is the total number of address used by the protocol. So how many address are there in this IPv4? We will have a look after this. A protocol use n bits to define an address. So address space is supposed to be 2 power of n, because each bit can have two different values, 0 or 1, and n bits can have 2 power of n values. So for IPv4 address, it uses 32-bit addresses. Okay, 32-bit addresses in terms of 0 or 1. So it means that the address space is 2 power of 32, or this number. I think this is a 4 billion. Okay, more than 4 billion numbers. So theoretically, if there were no restrictions, more than 4 billion devices could be connected to the internet. Okay, so there are 3 common notations to show an IP address. Means there are 3 common forms. Okay, so the first notation is binary notation, which is base 2 numbers. Okay, the second one is the dotted decimal. Okay, the dotted decimal, however, the base here is 256, and the third one is hexadecimal notation, which is base 16. Okay, now the first one is binary notation. So we know that the IP address has 32 bits. So for binary notation, it is displayed as 32 bits in terms of 0 or 1. Okay, and to make it more readable, one or more spaces are usually inserted between each octet or 8 bits. Okay, so remember that we also referred to octet as byte. So if you look at the example here, it has a space. Okay, it has space in between 8 bits. Okay, so this is an example of an IP address. Okay, we can also call it as 32-bit address. Some of the books also referred this notation as 4-octet address or 4-byte address. So the next notation is dotted decimal notation. Okay, we use dotted decimal to make an IP address more compact and easier to read rather than using the binary number, which we have to convert to decimal first. So internet addresses are usually written in decimal form with a decimal point separating the bytes. Okay, we will look at the example after this. And because each byte or octet is only 8 bits, each number in the dotted decimal notation is between 0 to 255. Okay, because there are only 8 bits. Okay, so the maximum number of decimal, the maximum value of the dotted decimal here is 255. Okay, So let's look at the example here. So this is the binary notation for the IPv4 address. If we convert it to the decimal address, it will become like this. Okay, so how to convert this from binary to the decimal? Okay, basically each of these bit here, okay, define 2 power of something. Okay, for example, at the position here, 1 is 2 power of 0. So the second position from the right here is 2 power of 1, and so on. So we take the value 1 here, okay, so add all these numbers together. 16 plus 8 plus 4 plus 2 plus 1 is equal to 31. Okay, so for this first 8 bits from the right, the dotted decimal here is 31. So it's just a simple conversion from the binary number to the dotted decimal number, to the decimal number. Okay, and for the binary number, we put spaces in between bits, but for the decimal here, we put dot. That is why it is called dotted decimal. Right, so the next notation is hexadecimal notation. So we sometimes see an IPv4 address in hexadecimal notation. Okay, each hexadecimal digit is equivalent to 4 bits. Okay, unlike the dotted decimal, we convert 8 bits to one decimal number. For the hexadecimal, each hexadecimal is equivalent to 4 bits. So this means that a 32-bit address has 8 hexadecimal digits. Okay, we normally don't put spaces or dots for hexadecimal notation. However, 0 adds here, or OX is added at the beginning, or the subscript 16 at the end, to show that the number is in hexadecimal. So if we put 0x here, okay, we know that this belongs to the IPv4 address in hexadecimal. Okay, to convert this, each of 4 bits here belongs to F. Okay, another 1110 here, if we convert to hexadecimal, it belongs to E, and so on. And 0 here is 0. So this 0s is to show hexadecimal number, or we can also omit this 0x and put subscript 16 at the end of the hexadecimal numbers. Right, let's see some examples here. Okay, change the following IP address from binary notation to dotted decimal notation. Okay, how you do that is by using the conversion from binary to decimal. So I believe you already learned that. Of course, this is compulsory for you to learn that before. Okay, so you change it, it becomes 129.11.11.239. Okay, so this is just some example. You can check your conversion with the example. Okay, the next example here, change from the following IP addresses from dotted decimal to binary notation. So this you have to use, you have to know how to convert decimal number to the binary notation. Okay, which is quite a lengthy process. Okay, so this is the answer. Okay, now to find range of address, because sometimes we need to find the number of addresses in a range if the first and the last address is given. Okay, some other time we also need to find last address if the first address and the number of addresses in the range are given. So for this case, find the number of addresses in a range if the first address is given as this and the last address is given by this. Okay, so how to find the number of addresses? Okay, we have to perform subtraction or addition operation in the corresponding base. For this is a dotted decimal, which is base of 256. So we have to subtract the first address from the last address in the base 256. Okay, so this is how to do it. Okay, so we get the last address. Okay, sorry, this is the last address, we get the range. Okay, so to find the number of addresses in the range and this in decimal, we convert this number to a base 10 and add 1 to the result. Okay, so first 0 here, multiplied by 256, okay, power of 3, because this is what we call dotted decimal in the base 256, and this 0 multiplied with 256 power of 2, this 3 multiplied with 256 power of 1, and this 255 multiplied by 256 power of 0, okay, which is 1. So add by 1, you will get the range of the address, okay, which is 1024. Range of address also means that the total number of addresses from this given first address to the last address, okay. So the knowledge on how to calculate the range of address or the total number of address here is very important, because after this you are going to learn about classless addressing, okay, in which you have to find the total number of addresses at a given organization. For example, given a first address or given the last address. So please understand on how to find this number. Okay, now we look at the IP address parts. Okay, we need to understand part by part on the IP address. Okay, so each 32-bit address of IPv4 address here is divided into network ID and host ID. Okay, basically it comprises of a variable length network portion in the top bits here and also host portion in the bottom bits here. Okay, the first part here is the network ID. Okay, the first part of the IP address. It is used for routing packets towards a network, and it must be known by every internet router. So for the routers, it will ignore this host ID part, okay, of the address when looking up the next hop. And routing is also is the same for all hosts with the same network ID. So basically, all the hosts in a single network will has this network ID portion the same value. Okay, so this is actually 32 bits. This is your IP address. Okay, so from here to here, the total number of bits are 32 bits. For the host ID, it identifies a host within an IP network, and all the hosts on the same network here will have the same network ID. And communication within one network uses lower layer mechanisms to deliver packets. For example, Ethernet and also ARP protocol, which we are going to learn later. Hosts attached to multiple networks or routers must have separate IP addresses at each interface. So a host typically has only one single link into the network. So when IP in the host here wants to send a datagram, it does so over this link. Okay, interface here is the connection between host, router and also physical link. So routers typically have multiple interfaces. For example here, this router here has 3 interfaces, and host typically has 1 or 2 interfaces. For example, wired Ethernet or also wireless 802.11. Okay, this is the interfaces for a typical host that is connected to the internet. Okay, when the network address part here is all 0, it means that this network, okay, for example here, if the dotted decimal address here is 0.0.0, it means that this network, so it is useful during initialization phases when actual network ID is not known yet, or when this part is all 1, okay, it means this is the broadcast address. Okay, next we go to the IPv4 classful addresses. Okay, so IP address, when it started a few decades ago, it used the concept of classes. Okay, and there are 5 classes which were introduced here in a few decades ago. Only in the mid-1990s, classless addressing was introduced, okay, which supersedes this classful addressing. Okay, classful addressing. So like I mentioned before, I introduced you to classful addressing so that you can understand classless addressing in the next lesson. Okay, and you understand the rationale to moving from this classful address architecture to the classless addressing. Okay, so we look one by one. Okay, we look one by one. For the first class, class A, the network here, the first bit here is 0. Okay, so this is fixed. The network, the first bit here from the left is 0. And the next 7 bits from the left is dedicated to the network. Okay, and the next 24 bits here is dedicated to the host. So basically class A is for a few networks and with many hosts. So this is for really large organization, okay, that has many hosts. For class B, okay, for class B, it is for medium number of networks. So the first 2 bits here is fixed. Okay, 10 is fixed to identify class B. And the next bits, 14 bits, belongs to the network or native. And the next 16 bits belong to the host. Okay, so we move to class C. For class C, the first 3 bits are 110, okay, which is used to identify class C. The next one is the network part, which is 21 bits, and the host part only takes 8 bits. Okay, so basically this is reserved for many networks, each with a few hosts. Okay, but for class D and class E, they are not divided into network ID or host ID because class D here is used for multicast. Okay, so the first 4 bits here, 1110, is to identify class D, and for class E is reserved for future use. Okay, so now we look at the total number of addresses, or we call it address space, in each of the classes. For class A, to calculate the total number of addresses, it is 2 to the power of 31. So why not 32 instead of 31? Okay, recall that for class A, the first bit we used to identify class A. Okay, the first bit here is already used to identify class A. For class B, there are 2 bits which we use to identify class B. So the balance here for class A here is 23 bits. Okay, so the total addresses or address space here is 2 to the power of 31 for class A. Okay, this is a number, very large number. And for the class B is 2 to the power of 30. For class C, it's 2 to the power of 29, and so on. Okay, so basically to find address space is 2 to the power of n. So n is the bits that define the address. Okay, n is the bit that defines the address. Okay, so in this figure, we can find the class of an address when the address is given either in binary or in dotted decimal notation. Okay, so this is the binary notation. In the binary notation, the first few bits here can immediately tell us the class of the address. And in the dotted decimal here, the value of the first byte can give the class of an address. So basically, the value of the first byte here, in the dotted decimal here, is converted from this binary number. Okay, so for the first class A, okay, it starts with 0. So for dotted decimal, it starts from 0 up to 127. So if you see any IPv4 address that uses classful addressing, which starts from 0 up until 127 at the first byte here, you will know that this address belongs to class A. Okay, if it starts with 128 to 191, it belongs to class B, and so on. Okay, in classful addressing, a large part of the available addresses were wasted. For example, here class A here it is designed for large organizations with large number of hosts. So one problem with classful addressing is that each class here is divided into a fixed number of blocks, and each block here has fixed size. Okay, for example here, class A here has only 1 byte that defines the network ID. Okay, and the 3 other bytes here, octet 2, octet 3, and octet 4, is for the host. So it means that it is reserved for a large organization that has many hosts. Okay, so which means that the organization should be a really large one to use all these addresses. Okay, so you can calculate by yourself the number of addresses for hosts. Okay, for hosts for in class A, B, C, and so on. Okay, so because of this fixed length of um, network portion and also host portion, many addresses are wasted, okay, if you use classful class. So this motivates we to use classless addressing instead of classful addressing. So in the next lesson, we are going to learn more about the classless addressing. Okay, so that's all for classful addressing. Thank you.